Okay, so what you see on the left-hand side is how the current consumption is changing versus the core frequency. Core refers to the processing core. So what you see is as the frequencies are going up, sort of the core is changing, and the blue and the red correspond to peripherals on the chip being all on or all off. So the peripherals in this case, sort of the gap between the two curves. On the right hand side, you're kind of seeing the same thing, except that now when it is in that very low power mode, and it's kind of a bit hard to read, but these numbers are a lot lower on the y-axis here. And there are similar other considerations that will come into play. Now, the main thing out here is we are only changing the frequency, not the voltage, because this particular chip does not have onboard circuitry to change the voltage dynamically. Neither does it have it on the boards. Okay, usually those kind of voltage regulators, where under software control you can change, are little bit rare to find on chip, and even on boards are often not there. But phones have it. So like on your smartphone, if you dive deeper into programming, at least on Android, for example, you can control the frequency and voltage both. Okay, so there are platforms where you can play with this thing, but it's kind of harder to come by with them. So now energy and power. I want to dive a little deeper because things are a little bit subtle there. So again, I hope all of you know power is energy divided by time. So average power is energy consumed over time, and power energy is integral of power over time, right? So that's from high school physics. Hopefully you recall that. So I want to just bring out what kind of things that we face. So this is kind of two old MCUs, mostly because that's where I have the numbers for, but kind of the story holds. One was when actually Intel used to make ARM-based chips, early like 2000s, 2000 2010 timeframe. So the 32-bit processor, MCU, consumes around a watt or so peak, can go up to a gigahertz. So pretty high-end as MCUs go, very high-end. This one is the chip that you find in Arduino's. Atmel microchip 80 mega 128. 8-bit processor consumes around a few tens of milliwatt and 10 to 15 megahertz in that range. So my question, which one is better for a low power system? Right. Everyone thinks right? Anyone think left? No? Yeah, it's a trick question, obviously. So you're smart, so you're going to say left. Okay. But then I'm going to ask why.
Because that's only the peak wattage or power.
Okay.
In normal operation would be a lot less.
No, okay, so that's one possibility. Normal operation may be, what if I were to actually operate it at 10 megahertz, right? We can perhaps try to get some number out here. 10 megahertz is a gigahertz divided by 100, so it would be 1 watt divided by 100, so I would be at 10 milliwatt. So that holds true, except it doesn't quite work that way, because what happens is if you look at the frequency versus power curve of it, it actually saturates at the bottom very rapidly. The reason is this is a complex chip, so there's a lot of stuff just on all the time. It's something called leakage power. Like whether you, even if you're doing nothing, it's going to consume that power. So, but point well taken. I think that's okay. But what about? Remember, we are talking about the story of energy and power. What about how much energy it takes to do a computation? Maybe this thing is more efficient at doing it, right? I mean, you might imagine it's a puny little processor. It probably doesn't do a whole lot of arithmetic very well. What if my arithmetic is 16-bit? This thing can jump through it easily. This guy will have to kind of handle it in 2 chunks and all. So if you throw real workload at it, what happens? So this is an example. There are 3 examples actually. FFT, floating point. You need it for FFT. What you have out here is execution energy in microjoules. It's hard to kind of intuitively relate to it, but just focus on the numbers. Left-hand side is what the 8-bit processor did, and the right-hand side is what. And this is a log scale. Okay, so 8-bit is, I don't know, seems like around maybe 20, 30x worse. Okay, story repeats, cyclic redundancy check, which is used for error checking. FIR filter, which is a type of filter which is used. Same story, all over. Okay, so which one is now better? (32-bit) is better, right? Okay, so clearly from an energy perspective, big processors win out. If I have a lot of work to do, then big processors' architectural efficiency, the fact that they're dealing with 32-bit chunks and all kind of things, win out. But that's not the end of the story. There's a third aspect also. So what you see out here is the following. I'm changing the power modes now. Okay. So first two plots are for the 32-bit, a platform built using the 32-bit one. So in this case, you see that suspension, going to suspend mode or coming out of suspend mode costs me a couple of hundred microseconds and around 63 microjoules of energy. So going to suspend. Resuming from the suspend mode, so this is kind of showing coming out, exiting suspend mode. It takes around 10 milliseconds. You might ask, why does it take 10 milliseconds? Because that's a 32-bit processor running Linux. Boot up time after it's coming out. Okay, now this is around 10, 12 years old. Now things have certainly improved, but the point is a complicated OS takes time to make up. Okay, 4 millijoules. Sleep mode, 120 milliwatt power. This guy, resumption, much less energy, microjoules. Suspension close to 0. Sleep mode, 30 microwatt. Here, sleep mode is a milliwatt. In fact, this thing is consuming more in sleep mode than this thing consumes in peak power mode. Okay? So when you are looking at across platforms of different architectural complexity, the big platforms give you efficiency, but they are lousier in terms of power management. Okay, that is when they're asleep, they consume more power, and it takes more energy to come in and out of power, in and out of a deeper sleep mode. So main moral of the story out there really is that you have to kind of figure out what is kind of more important, and ideally what you would want is something which is super agile, something which consumes close to 0 when you are asleep, can come out of a sleep mode very rapidly, and does things very efficiently when it's up. Unfortunately, such a magical thing doesn't exist in a single device. So we have to do some tricks to mimic that. Generally speaking, if you have a car which is optimized for going long distance with high speed, whatever, doing high speed efficiently, it will probably be gas guzzling at the lower speed and vice versa. Right? I mean, that's peak performance and sort of commute performance are kind of two different performance optimizations. The same story out here. Okay, so what then should be our goal? So before diving into it, we're kind of the midway point, so let's take a 3-4 minute break, 5-minute break, and then we start.
Model that we can buy on the website, so we should get the break on so that
if you buy the new separate, then you can get
sorry, 89.
Yeah. So you buy the $49 for the breakout is 39.
And then
The only thing you missed then is
the start. And the Raspberry Pi, the breakout mode alone is not immediately available. That is one way that I mean, it's just
oh, it
does.
for $10 in Amazon. The only thing is replace a lot of you'll find them for $10. The problem though is I think it may not be available with cheaper shipping and all. You might want to look at Arduino, sorry, at Adafruit. Out of stock. Adafruit has a $14 version with you might want to look at Mauser, Digikey, SparkFun.
Where are these slides?
If you go on Piazza and you go under resources, and then you should see them on the slides, lecture slides.
Oh, it's right there.
Yeah.
Okay. And then are these released before or after
Yeah.
lecture?
I release them before the lecture. The only thing is that lecture 2 slides, I mean, sometimes I incrementally update them because from one lecture to another. Yeah.
Yeah.
It's also my department. That's why I was wondering. Like,
No, we are looking at the CS. You should look at the ECE section. So when a course is cross-listed,
Yeah.
it's usually closed in one department and all enrollment is to the other department. Okay.
okay.
So it's the same course.
Right.
It's just that you have to register through ECE M119.
Okay, cool.
Okay.
Okay, thanks so much.
When I see this chip, does that mean it's pretty similar?
Yeah. It's increased.
That means
Yeah.
to work with why would we need these two stuff?
I think you need the Hexavere sooner than this one, but if you can get both sooner, the better. Yeah.
Talking about interrupts, right? So let's say if you have an interrupt from a computer, right? It has multiple cores, so even if one goes to sleep, one can still be idling, waiting for it. For this, would the only way to make it back up be via some kind of hardware interrupt? Like
Or a
press
timer.
button?
Or a timer. Internal timer. So you tell the timer, wake me up.
But the timer is also send like a signal, like a hardware signal. to
Yeah,
it.
so send a hardware signal.
Okay. Okay.
So basically, most of the chip is for to sleep. There is some timer or some
Uh-huh.
anti-autonomous chip still running.
That's the one. Okay. So the entire thing can go down, but then you have to.
Details depend. So I mean, this is a new chip for me as well, so I don't know all the details, but all sort of variants exist.
Okay.
But generally speaking, it would be that most of the peripherals in the processor are going to be put to sleep, and there will be some timer and
Okay. So one part.
No. Sysdig timer is for the operating system. That's usually separate. Yeah. I mean, again, depends, but most MCUs have some separate timer for it. Okay, let's restart. So there was some question about interrupts and like how do we wake up out of this. So the source of interrupt could be outside, like pressing a key or whatever, some sensor which is monitoring, or it could be just a timer. Before you go to sleep, you set a timer saying wake me up in whatever 5 seconds, and then the timer does it. Usually these chips have some timer or something like a timer which is designed for such wake up and all. Most like if you look at like Apple's chips, for example, they have a whole power management module whose job is to do these kind of things. So it kind of is the only part of the system which will stay up, and then everything else can be put to sleep. So these are complicated things. So I unfortunately cannot give you a general answer. These are exactly the kind of things when you read the data sheet. I think usually I find the most interesting systems of an MCU. Processor is a processor, it doesn't really matter. It's the timer system where all the timer stuff is located, and the other one is the power management. I think these two are very interesting and useful to understand about particular device. Now, the other thing is not all capabilities of a hardware may be exposed by the OS. Operating systems are designed for portability and general purpose usage, so some of these things are you can exploit only when you are willing to write down. Okay, so before the stop time, before the break, we kind of talked about that how kind of there are these different things which come into play. There's absolute power, energy, and then there's switching back and forth between the different modes. There are relative efficiencies differ across things. Complicated systems, big systems, tend to be efficient but lousy at transitioning, and obviously lower power. And small systems, smaller 8-bit type things, are kind of on the other end. So what that leads to is that kind of what in sort of those of us who work in this area, we call it energy proportional systems. That is, the holy grail is to have a system which, when the workload is more, consumes proportionately more power, consumes proportionately more energy. And when the workload is less, it consumes less. When the workload is zero, it should consume zero. So it should basically be a linear function, whatever, A times load, okay? That's what it should be. So like, for example, it's a smartphone. If you look at what happens to a smartphone, the user is swiping, and then maybe you have some cool and animated widget, which every second kind of does something, and also you see these bursty nodes, and then in between kind of not much is happening, right? So this kind of workload is quite common. Or you might imagine some other device where every time the sensor data comes in, it processes and goes back to sleep, right? So this kind of a bursty load is quite the norm. And in fact, the other thing is, if you see that average load is actually pretty low, right? I mean, plotting it this way. So so question for you: do you think I should? I mean, if let's say this average load, I don't know how much it would be, but let's say it's 20%. Do you think I can get away with a processor which is 5 times slower, and then 100% workload all the time?
The performance would be affected.
In what manner? I mean, I'll still finish all the tasks.
Yeah, but whatever should be happening within the specified amount of time, it would probably be taking longer if you're going to.
So timing constraints will be violated, right? I mean, so the challenge that we often face is to meet deadlines, latency, like having a small short latency. We have to have more powerful processors or systems generally than we need, right? So the reason you have a more powerful engine in your car is not because it helps you when you are cruising, it helps you in the acceleration, right? So it's the same thing out here. It's the time to sort of rapidly go up and down. Okay, so I can't get away with so yeah.
How do they actually arrive at these kind of trade-offs like energy versus latency? Like, isn't it very hard? Like, because given that it's in a smartphone scenario, it's going to be variable workload. So how do they actually arrive at?
So you have sort of, you collect data about typical workloads. So like when you talk to people working at companies like Qualcomm and all, right? I mean, what they have is they collect data from phones that they had, instrumented phones. So they know how users react and all, and then they use that. But that only gives you an average model. Users are different, workloads are different. Someone may be playing more games, others don't. So again, additionally, you want to create systems which adapt to a particular situation. And that's where, as I was referring earlier, that nowadays the fashionable thing to do is to use machine learning, AI, and these kind of methods. Okay, so there's a benefit of that. Okay, so goal is energy proportionality. Question is, how do I achieve it? So I already told you that no single processor we can design, generally speaking, or holds true broadly, I mean, for systems, cars, whatever, which will be energy proportional in the sense that consumes zero when the performance is zero and consumes something is not strictly linear. What you find are processors, like I can get a big processor and using dynamic voltage frequency scaling, which I talked about earlier, maybe it will span some band. Okay, so higher performance comes at a higher cost, but it's going to go through something. And when it will saturate and you go down to zero load, but the processor is still up, like power on, it will have consume some power. So we'll have that. Well, what can I do? Well, one thing I can do is I can take another processor and hopefully it has a different power performance. Okay. So now I have two processors. And one of the things I could do is I can have these two processors have the same instruction set. So instruction set is the contract between the software and the hardware. That is, if two processors have the same instruction set, then I can run my software on both of them. But there are many ways of implementing that instruction set. When you take a computer architecture course, they kind of talk about like I can have caches, I can have prediction of branches, I can have all sort of funky stuff which helps speed up the processor. In fact, how many execution units I have within the processor, do I pipeline it? There are a whole bunch of considerations. So the same instruction set architecture can have multiple implementations ranging from small agile ones to kind of big but very powerful, very efficient and high workload ones. So I may have a separate code which, if things are all well, might have the same ISA, same instruction set architecture, or alternatively may have a different instruction set architecture, totally different. One may be Intel, one may be ARM. In which case, I need two versions of my software, one for Intel, one for ARM, and deal with the resulting messages. But main thing out here is that nowadays you can find processors with the same instruction set architecture, but different details, different microarchitecture, which span things. So, like for example, you can find a whole bunch of different ARM processors which sort of have this characteristic. Big processor which is optimized for high performance, and then some sort of simpler versions of that which is optimized for a lower performance. And I combine the two, and now I have a challenge that I somehow need to move back and forth between these. So how do you think I can do that? So I have now two processors which collectively are giving me more energy proportionality than otherwise, right? I mean, I'm beginning to mimic two of these, and I can extend the logic maybe a third of this. Let's imagine, for simplicity, they have the same instruction set. Sorry, software. So what do I need to do? Like, what might your strategy be?
Probably through interrupt, like since they use the same send and interrupt if you want to like switch tasks.
Okay, but when would you? The thing is, I have to decide where do I want to run it, right? I mean, so I need to have some intelligence to say, like, can the workload be handled by the lower end processor? If so, I should better run here, right? But on the other hand, so those bursts are probably better handled out here. So some sort of thing, right? I mean, I start monitoring how much load am I putting on the processor, and if it turns out I'm putting too much load, maybe it's time to move to the bigger processor, or maybe I can predict. Maybe I know every second this high performance task comes in. I learn that, and then I make sure that the big processor is ready when I predict it's going to come, right? So I can play all those kind of games. When I say I and like the software, it's not really your application that is going to be doing it. It's the operating system which is going to be doing it. So the operating system is the one which is going to be playing all this moving around of the tasks. So, and I can even have, like I said, even a tinier thing, more sort of yet another processor which is perhaps even more, somewhat more detached and all, maybe harder to switch to and all, but I can have that as well. So oftentimes in these systems you find multiple processors. Sometimes they have the same instruction set, sometimes they're loosely coupled, and there would be various strategies to wake them up. Our little watch has two processors in it, right? It has the Bluetooth processor and it has the bit processor. Well, part of the reason is the Bluetooth processor is there because it is perhaps doing something very dedicated for that. But my guess also is because you want to put the whole thing to sleep and then be woken up when a packet arrives over the Bluetooth link. So that little processor can be up and running.
I'm a little confused on how like adding a smaller processor, I guess like improves the energy consumption.
So since this processor is it's basically letting me operate over a larger range of power performance. If I have a big processor, right? So I have to. This is the lowest I can operate at. But let's say my workload is here. Okay, then I will be needlessly paying this much energy, more power.
But when the bigger cores, like I was technically on sleep mode, wouldn't it still consume that much power at the same time?
Oh, so in this case, when we what this is showing is the active mode of the big processor. So if I'm running out here, I'm going to put the big processor into some sort of a sleep mode,
Which is significant.
which is going to be lower than this, but it's not going to be zero. Okay, and if you know that I'm really going to go to sleep for a long while, then you can even power this thing off. The only thing is the wake up time will be lower, right? So which mode you put this thing in is you. So let me rephrase. If I just keep it idle, then there is no win, obviously, for the reason that you are saying, right? So I have to put it into a lower mode, lower power mode. But how much lower can I power it off, or do I need to put it into some sort of a sleep mode? The idea is hopefully it's low enough that it's somewhere close to the
So you mentioned that you put in sleep like powered off mode. There's a wake up time, but wouldn't the other processors be able to handle the work while the other ones are powering up?
Yes, and you would make use of that. Indeed. So you kind of do a handover of the workload. So you can hide it. The only thing is the following: that if this is too slow, and whenever that comes, you have some very tight latency, then you're going to trouble. So it depends upon what the precise latency and which one the wake up time is. And the other thing to bear in mind is that during wake up, energy is wasted. Okay, so because the act of waking up is taking time, and therefore that's sheer wasted energy cost. A good example: take a hard drive. When you start using it, it spins up, and before it has spun off, you can't use it. All that thing actually, hard drive consumes joules of energy during that time, right? So that time when processor is waking up and all is purely wasted energy. So you do want to avoid mistakes in that prediction. Okay. So we combine things, and then kind of the idea is that what happens as a consequence is when, for example, the user is swiping, maybe the big processor kicks in, and another time, the smaller processor is the one which is running. And this is routinely done nowadays on phones and a whole bunch of embedded devices, but these are still kind of more higher end embedded devices. You'll not necessarily find this capability in low end stuff. So. Good example of this. So this technique is called big dot little. Big processor, little processor combined together. And one of the early chips which had this thing was a chip called Exynos from Samsung. And what this chip had was it had 8 processors. 4 of them were big. Out here. So these were the big part. And this was the little part. Okay. Specifically, these were so-called A15 processors, and these were the so-called A7 processors. These 1.8 gigahertz, 1.2 gigahertz, all those things matter. But main thing is 2 processors of different capabilities, but having the same instruction set architecture. Okay, but different microarchitectures, the underlying implementations are different. And then of course, the rest of the stuff is these things that go on to a typical MCU, various peripherals and all. You could also see that more cache out here, and also this heavier duty thing out here. Just to give you a sense of what these 2 processors look like, so A7 is what is called an in-order processor. Specifically, what it means is it basically executes instructions precisely in the order they were arriving. A15 is out of order processor. What it means is that when the instructions are coming in, it looks at them and it says, can I go ahead and execute the next instruction because this instruction needs more time? Because sometimes instructions do not have dependency. The next instruction may already have the data it needs to process it. So out of order can speed things up, but are costlier to implement. Pipeline. So that's the assembly line concept that things are arriving and different stages of the processor are working on it. This has a shallower pipeline, 8 to 10 stages. This one is a much longer pipeline. So it can give much better performance on long workloads. but at a significantly more hardware cost. Queues. Instructions come and sit in a queue to be processed by the hardware. Here there is a single queue feeding into 5 execution units. Here there are 8 execution units, each one of them is a queue. So it has a lot more hardware. Net consequences, this guy on an average, on a peak basis, can do 2 instructions per clock cycle. This guy can do 3 instructions per clock cycle. So gains performance. And likewise, now there are ARM processors which are meant for like data center use and all, and they can go even more. So little slower, but more power efficient because it has less hardware. Big, high performance, it's more power. So with all of that, going back to where do these 2 processors reside? So roughly speaking, for the A7, its operating point is something like this, and for A15, the operating point is like this. At the lowest operating point, this thing takes more power, and that gap that you are seeing out here, this gap is because the big processor just has more transistors and all that, just leaking away power. But it can go to performance, which this guy can never do. So the strategy of combining things is a very common strategy to achieve energy proportionality in this manner. That is, you take 2 processors of different characteristics and then kind of stitch them together. There's a second strategy for achieving energy proportionality, which works in some cases. If I have tasks which can be subdivided easily, then I can have multiple identical processors and just keep some of them alive and rest not. So like, let's say I have to process images, okay, and the number of images that come at me may change. What I can do is I can have a bank of identical image processors and just keep sufficient number of them alive at any given point in time and the rest asleep. So I can, and if I suspect that more images are going to come at me, then I'm just going to bake up more of the processor. So that's another approach that could use. But this big.little is something that you see out here. Now going back to this chip, you can do both now. So if you see I have 4 little code big. In fact, the way this chip works is a pair of little big is sort of coupled together. And I have 4 such clusters. So I can have, in a lowest power mode, I will have 1 little on. Okay, and the way this particular chip was that I could keep the other, that I could not have a little and a big in a given pair simultaneously on. Okay, so it had to be a big or a little, but then across those 4 clusters, I could make any given choices. So I could have like 2 big, 2 little on, and things like that. So I could do that scaling also out here. That is, how many of those pairs I activate depends upon what work I am expecting. So quite scalable in terms of its characteristic, but you have to go to these games because it's very effectively, it's impossible to design hardware which can scale, because if you want performance, you're going to you have to pay for it by a more complex hardware.
Can actually a bloated OS implementation on Samsung, like these phones, I mean, they put the Exynos on the phone, so can it actually kind of defeat the purpose of this big little?
Sure. So all of this is assuming that compiler and operating system are going to do a good job at it, but if they don't, you have a problem.
They actually face a lot of flack for the, for overburdening the Samsung like in their initial.
Actually, I don't know about Samsung, but Qualcomm had a lot of flack because their previous chip, the whole big little stuff actually didn't work very well, and the chip overheated quite a bit. Yeah, 835. So sometimes bad things happen because all of this requires a fair bit of complexity and all kind of sitting in there. So not necessarily easy to get it right. So power management nowadays is one of the big complicated aspects of embedded processors. Yeah.
Quick question. So we've had multi-core like laptop grade processors for 20 years now, right? Why did it take so long for them to for and like multiple levels of
Big dot little?
processors. Yeah.
I guess part of the thing was simply availability of sufficiently different processor cores. Remember, firstly, laptop market was largely owned by Intel, and Intel didn't create anything. Okay, so all of these things emerged when ARM moved up to begin to produce more complicated things. Okay, so for a long while, ARM basically was playing for the standard mainstream computing. They were playing with the A7 type things. ARM also has a lower end family, the processors that we are using, Cortex series, but they do not have the kind of things you need for providing operating system protections and all. So they were not really meant for this market. So it's only in recent times that ARM moved up, became A15 and now even A53 or something, which are kind of more even more powerful ones. So that began to happen there. Also, I guess power considerations and all kept things at the low end for the longest while, but then demand for doing more and more on our smartphone has resulted in more powerful processors. I mean, now we have 64-bit stuff and all, right? I mean, it's all because we just expect a lot of these devices. Okay, so yeah.
Like, you mentioned about the backup processors.
Like here.
Yeah. So is it like to even out the optimization, or I mean, will it achieve the same as a single processor?
No, so it's basically so intuitively what this says is there are two ways I can achieve energy proportionality, right? I can have a whole bunch of identical things, and the fraction I keep up dictates how much performance I have. And the other is I can have different things optimized for different points in the power performance space, and then which one I keep up is going to dictate that. So workloads which are divisible into identical chunks benefit from how many clusters you have, or even workloads which would just be mapped like within a task. And then big dot little is more about the nature of the workload. So yeah, so they give you both the dimensions and sort of get to play with that. And very common nowadays in embedded systems is to have some tiny little processor whose job is to just, when everything is asleep, it just keeps listening for something interesting to happen, and then wake everything up from it. So how do we manage this process if I have these big dot little? So how might you do it? So one approach is that kind of very loosely mentioned it earlier, which is I keep an eye on how heavily loaded my processor is. And if the processor is getting close to its full capacity, then I would say, aha, it's time to wake up the big guy. So I could do that kind of an approach, and this is an example of that, where essentially what I do is I keep an eye on what is happening, and then at various times I kind of trigger a transition to the big processor, and then if the big processor workload is such that I can go down, then I transition. I move back from the big processor. So basically, I keep an eye on how my tasks are doing. But what also happens is, whenever I have to move from one processor to another, it will take some time. There is going to be cost associated with it. I have to move data from one to another, right? I have to activate the program. So there's always going to be some overhead and all. So all of those things are going to cost something as well. Something one has to keep in mind. We'll talk more about it later in the course, but right now, just at that. What all of this adds up is the following. So this is a whole bunch of different tasks for a smartphone, and what you see out here is what percentage of saving we have relative to just running things on the big processor. Okay, so if I do this big dot little using that weighted average strategy, so what you see is that if I just look at the CPU power, okay, that's the blue curve, 75% saving, 75% saving, 40% saving. So it's pretty substantive saving. So I'm basically saving that much energy or that much average power relative to just running on the A50. But to drive home another point, just focusing on the CPU power is only part of the story. I may make CPU is super efficient. What about rest of the system? Rest of the system I am not able to put to sleep necessarily. So the actual system saving is usually going to be a lot less. So the red one shows that. What is the saving for the whole chip, not just the processor part of it? And you see that at the chip level, I have a 30% saving. Still significant, but a far cry from 75%. And similar numbers out there. So I guess the main takeaway that I would, two takeaway. Firstly, big.little works, I mean, as you can see, but the other part is saving, CPU versus system. These are two very different things, okay? And other parts of your system can be bottlenecked. In fact, I can reduce the CPU power to 0, and I'll still have other stuff on my chip and all, which will consume things. So one has to kind of keep an eye for that. Okay, so whenever you are evaluating something, a strategy and all, keep an eye for its limits, because if my CPU consumes only 10% of the system power, and I make the CPU to be 0 power, while the CPU power seems to have improved a lot, but the system power will only gain maximum 10%, right? So one has to keep an eye on like what are the important things. Okay, a lot of times you will find that your embedded systems are limited by other things. For example, very loosely, ignoring sensing and all, embedded systems, you could say, do 3 things, right? They process data, they store data, and they communicate data. Processing and storing in RAM tend to be cheaper. Communicating wirelessly tends to be very expensive. We'll talk about later, but loosely speaking, if I were to send a bit from across the room versus execute one instruction, sending a bit across the room would probably be 10 to 100x more expensive. Okay, which means that I can do maybe 100 instructions and still come out ahead versus sending that bit. So communication tends to be very expensive. What else do you think on a device like your smartphone is expensive from a power perspective? Graphics, okay.
Keeping the screen on.
Screen, yeah, screen is a huge thing. In fact, battery numbers that Apple and all quote assume that your screen is on no more than 5% of the time. Okay, because and screen power is affected by what? Brightness, right? So particularly like, if you have an OLED screen, then it's emitting light. If you have an LCD screen, then it has a backlight and it's brightness. So brightness plays a role. Color versus black and white play a role. So many phones have, I think Samsung phones, for example, in a low power mode, they switch into monochrome. Okay, so because color. GPU, which sits behind the screen to kind of power it up, to provide the graphics and all, so you can have a high performance mode versus low performance. How rapidly you are refreshing it. Okay, so screen is very power hungry. Radios are very power hungry. Writing to flash memory is very power hungry, because when you write to flash memory, it has a characteristic that even if 1 byte is changed, I still have to write a whole bunch of bytes. So flash memory can be very expensive. So main thing that I want to take away is that this is only looking at CPU versus the chip. By the time you think of the whole system, the gains are even more modest. Okay? So this is something to keep in mind. And when you evaluate things, you should really evaluate the whole system, because that's the true picture. So this is another example of somewhat modern. I think this is like 3 or 4 years, 3 years old now. A picture of a 3-year-old Qualcomm chip, but I wanted to show that they have kind of a similar multi-core kind of a structure. But the other thing you would see is they have a whole bunch of other processors. They have these DSPs, which are those domain-specific processors. They're picking up some of the workload. They have a GPU and 2 processors. Okay.
Does Qualcomm also use ARM, or do they have?
Yeah, Qualcomm also uses ARM. So ARM has 2 business models. One is you can license from them a design. Most companies do that. they license a design. And then there are those who license the architecture. What that basically says is that these companies are going to implement their own designs. My understanding is that there are just 3 or 4 players in the world who are architecture licensees: Apple, Samsung, and Qualcomm. Of these, even Qualcomm now seems to use, at least on the recent chips, ARM designs. Apple is the only one which designs its own ARM processors, okay, from scratch, so that they can optimize the hell out of them. So, with proprietary circuit techniques, they can make modifications and stuff like that. You could see like these things like A7 and A15 and all these are standard you can buy from other vendors also. So I don't know about this particular chip, but the Samsung chip clearly they were, yeah, this one. This is just a standard ARM design. What you get from them is kind of details on the design. Then of course you create your own selection, and of course you can surround it with your own goodies. Okay, so let's see, how are we doing on time wise? Yeah, it's at 9. So one very important aspect of MCUs then is, besides power, the other one is interfacing with peripherals, external world, and things like that. And I wanted to talk a bit about that because that's the other thing that sort of when you are creating your own systems, as most of us end up doing, and this is how do you connect things. And I just want to put out like the way I use these terms because it's not necessarily uniform agreement on it. So there's I/O, and sometimes you'll hear I/O interfaces, sometimes you hear communication interfaces. Very loosely, I use the word I/O to refer to when I'm having the MCU talk to peripherals, nearby things. Okay, nearby peripherals, a sensor talking to the MCU, stuff like that, and or sort of physical world, motor and stuff like that. Communication, normally I use it when I'm talking longer distances over some sort of a network, but the two sometimes same techniques get used for both. So like your Bluetooth radio sometimes is used to connect a sensor to your phone, but it can also be used to exchange files between 2 phones. Okay, so sometimes similar techniques get used. So for now, I'm going to focus more on the I/O side of story. That is, how do you talk to, what are the different things out there to talk to peripherals and all of different types. And just wanted to show you the kind of things which are out there, partly because when you, let's say in your project and all, if you want to pursue some certain kind of sensors and all, you would see sort of these terms and all, and hopefully it will give you a sense and also the underlying methods. So again, the thing to note is that even in our little FlexiWare device, there is a whole bunch of peripherals that are actually on chip, right? I mean, and then a whole bunch of things on board. So on that board, there are a bunch of other chips which implement different kind of sensors. There is a accelerometer plus magnetometer sensor. There is a gyroscope sensor. There is a barometer and temperature sensor. They happen to be also made by NXP. There is a humidity and temperature sensor. There is an ambient light sensor, and then there is an optical heart rate sensor. Those of you who have smartwatches or Fitbits and all, those are little LEDs at the back, which sort of measure the blood flow and from that things. Okay. So let's walk over it. Accelerometer and magnetic sensors, they are measuring 3D acceleration and magnetic field. What are they used for? What are they useful for? What all can you use an accelerometer for?
Number of steps.
Number of steps, okay. What else? Motion detection broadly of any kind. You can in fact integrate acceleration to get velocity, integrate velocity to get location. It is very noisy, but you can, yeah.
Your screen orientation.
Screen orientation. In fact, that's why it was originally there when iPhone had first come out, and then people used it very in creative ways. What else? What else can motion be used for? So motion relates to a lot of behaviors, or human behaviors, right? On a wearable device, if you're smoking or drinking or shaking hands, there are all these kind of things. So you can classify motions into various kind of behavior. Okay? Magnetometer, it gives you a 3D magnetic field. What can you use that for? Compass, north, south, right? I can do that. What else? Huh? Gravity. Gravity direction. That you'll get from accelerometer actually, right? Because that's acceleration. So if you just put it flat, one of the axes is going to be 9.8 meters per second square, and that you can calculate. But magnetometer can tell you, if it was very precise, the angular angle related to Earth's magnetic field. Unfortunately, Earth's magnetic field is not very well mapped, and magnetometers tend to be not very sensitive. But if you have a very sensitive magnetometer, and if you are like US Navy, which has mapped the planet, you can actually figure out your 3D location from magnetometer alone, but not with these. Gyroscope. What does gyroscope measure? Angular orientation. No. Angular velocity. That's what gyroscope measures. Gyroscopes are used because so that you can keep the always figure out where the orientation is. So when you're looking at a rigid body, something like this, right? How many dimensions do we have to fully describe it in 3D space? Three. 3 will get me center of gravity, let's say, and then I could be anywhere, right? So 6. Roll, pitch, yaw. So x, y, z, roll, pitch, yaw. 6 things, right? So by taking these things together, gyro, magneto, and accelerometer, you can actually figure all of them out, and then you can kind of do things. Okay, so and that gets into, I guess, to fully understand it, you need far more advanced courses, but there are a lot of packages and all around for you to just help out. So kind of think of it as somewhat of a black box functionality, but it's not magical. MATLAB has it. Okay. Question?
We have these like 10 degrees of freedom. And, like, I mean, do they even?
No. So when you hear 10 degrees of freedom and all, what you are referring to is how many channels of sensing we have. So like oftentimes you will see a single board or a chip which will have accelerometer, magnetometer, and gyro, and they will call it 9 DOF. Okay. Sometimes they will have barometer also on it, and so because barometer gives you altitude, absolute pressure gives you altitude above the sea level, so then they call it 10 DOF. Okay. But from that, whatever useful you are deriving is different. And so when I'm saying that to fully characterize the rigid body, I need 6 DOF. Then, that's you can derive those 6 DOF. You can track this over time. So some of the work that sort of like, just to give you an example, one of the projects in my lab is the following, that we're trying to do some workforce monitoring and sort of people wearing these smartwatches. Can we infer how they are typing? Because as you type, sort of kind of move your hands around and all. So by looking at the data from accelerometer and gyroscope, we try to infer, are you pressing the space key, how many characters per second, what is the complexity of words that you're typing, those kind of things. Now, so we throw this data into sort of machine learning algorithms or training data to figure out this. So all sort of cool stuff you can do with these things. Barometer is interesting. It's ostensibly is meant for measuring weather, but it actually also gives you altitude. And in particular, these barometers are often very precise to give you pretty good change in altitude. You can detect things down to a meter or so of changes. So let's say I were to give you a device which can measure altitude changes to a meter. What can you do with it? What kind of things do you think you can infer from it? So, yeah, go ahead. Huh?
Make an aircraft.
You will make an aircraft? No.
Yep.
In
About aircraft.
Yeah, so I can control a drone, for example, right? I mean, I could see whether it's getting how much it is falling and all, right? Okay, so I could certainly do that. I could detect floors going up the floor, down the floor. I can see what my topological profile is, and then map it against some mapping data, topographical data from Google Earth, and then see where in the world I am. Right? I mean, like for example, let's say you walk around the campus, you come next to Bolton Hall, there's a staircase. How many places on the campus have that kind of a particular pattern? You immediately narrow yourself down, right? So it reveals something about location. So the reason I'm sort of bringing it out is that Hexaware is a pretty powerful device. When you think about cool project ideas, think about these sensors. What can I do with it? Okay. And in particular, as you look for project ideas, I want you to look at this conference called UBComp, which is the main conference. It's called ACM UBComp. Okay, it's one of the top conferences where people publish work like this, like using these kind of sensors and all, what kind of cool things I can do. And in the process, you will have to figure out how to process the data using machine learning kind of methods and all, which I will also point you to and talk a little bit about in the course as well. Okay, so hold on. Then I have a radio chip, which also needs to talk. So how do these things talk to, right? Clearly, the MCU needs to have ways to connect to all these things. There's a battery charger and a whole bunch of other stuff, right? So all of these things need to talk to each other. So fair bit of diversity. These different things have very different requirements. Data rates are quite different. Some of them require very low latency. How well you are synchronized. Sometimes I have to like do things together on more than one peripheral. How am I accessing the data? Is it just a stream or is it like random locations in some memory? You have constraints of pins because all these devices have pin constraints. If you have too many pins, then you need bigger packages, and that would be very costly. Power supply requirements. Typically, when you are dealing with peripherals from a processor perspective, there are three kinds of things that you want to do. One is you want to do sort of get and set parameters. You want to ask a device, set the sampling rate for the accelerometer, or what's the sensitivity. So I want to read and write certain kind of parameters. Second is I want to transmit and receive data. Like for example, I tell the radio, send this packet out, or get this packet coming in. And finally, enable or disable functions like turn the LED on, or whatever, shut the transmitter off, stuff like that. Very broadly, these three kind of functions. And all of these will somehow get mapped ultimately to some software call by your operating system, which your app will call. But deep down, it's basically a bunch of registers which you have to read and write to, bunch of memory locations, in effect, to a special memory location on these chips, which you have to access them somehow. So how do we go around doing it? Well, first thing to ponder about is the following. So I said these devices have registers, which I'm going to read and write to. They're like areas, memory areas on these devices, which through software I'm going to say read or write in order to accomplish those things. But on our computers, we also have data and program memory. So my question for you is the following. In what ways are these two kind of things different? Can I think of my I/O device registers just like I think of my data program memory, or do they have some different characteristics?
Sometimes these data or program memory could be just read only.
Okay, sometimes this thing can be read only, so can this. Right? Sometimes it could be read only. Oftentimes these devices have some identity register. You can just read it. What's the identity of the chip? What kind of things you think? In what ways these might differ? What kind? Or think of this way: how do I handle this data in program memory and? Okay, so that's a great point. In general purpose computers, for sure, I handle these things in bigger chunks, whereas these tend to be relatively kind of few. So absolutely true.
That the operating system usually handle data in program memory, whereas you, the programmer, have to physically go into the I/O device and get data out.
Actually, it would be the opposite generally, because you don't want programs, application programs, to be mucking with the hardware directly generally, right? I mean, because they can cause a lot of damage. And all. So it would actually be the opposite. Devices you try to protect more. So now, having said that, a lot of times we don't have much of an operating system. So in which case, what you're saying is absolutely true.
The device data could have some sort of periodicity that's not there.
Okay, so there might be temporal patterns out here, right? Sample data is coming every second or something like that, right? I mean, so that, okay, great point. So that's true. When we do data in program memory, we do caching, right? How do caches work? Not all of you would know of caches, so cache, basically the idea is, since reading and writing to the memory is too expensive, so there's a faster memory which is closer to the CPU, and when I read and write, I kind of read and write to that, and then something in the hardware takes care of actually reading and writing from the memory. Can I do that? Can I do caching with these things? Like for example, I can't, right? Because in a data memory, I can say write to this memory, and then the hardware just says, okay, I'm going to put it in the cache and write later. And as long as it gives me an impression that it wrote it correctly, I'm fine. Here I say write to this thing because it's going to turn on the LED, and it doesn't write to it, then there's a problem, right? The other kind of things also similarly, right? I mean, so when you say write, you actually want it to be written. When you are reading, don't just give me the value in the cache. Actually go and read it from the device because I'm looking for the actual value. So caching becomes pretty problematic with this. More challenging is the fact that while data, I can roll back. Like if I make a mistake, I can go back to a previous value. But I cannot undo what I did to the physical world. If I ask the robot to do something, I cannot undo that, right? So I can't undo the physical things. So a lot of stuff which we get away out here on the data program memory, I can't get away with the I/O devices, and therefore they need to be handled with appropriate care. So we're going to talk about that on Tuesday. So tomorrow Amr is going to do the TA section. He wrote, but just in case something happens, I'm going to come and do it. Okay. So see you guys.
Are you still gonna have your